So as Juan said, I'm going to be talking about llm.c. That means I'll basically be covering the framework on a high level for those of you who are not familiar, and I'll assume most of you are Pythonists and not that familiar with C, so you'll see some C code. But like heads up, do not try to analyze the code snippets. There's too much code there. It's just for more of a visual guide than anything else, okay? And so I'll cover the framework, and I'll also cover some of the common efficiency techniques that we use to make it go burr, as you'll soon see some of the numbers compared to PyTorch and whatnot. Okay, so first of all, who is the team? Basically, the project was started by Andrei Karpathy, who I assume all of you know. And there is a couple of us who are basically the main developers, research engineers, however you want to call us. The two of them are called, well, one is NGC92 because being Anon is cool, very cool now on X and on Discord. So I don't even know the person's name, but he's an amazing cracked GPU engineer. And then there is Arun, who used to work at Apple, who is also like amazing CUDA programmer. And there is me. I would put myself in the same bucket as Andrei Karpathy, which I know is not the best thing to say out loud, but in the sense that we are both generalists, and that's how we've been contributing to the framework. So they were kind of focused more on the CUDA side of things, and we were doing everything else, including helping around CUDA a little bit. So it was very cool to have Andrei like tweet me out, and also the folks I just mentioned. And you can imagine after Andrei tweets you out, you get a lot of crazy notifications on on X. And so yeah, we basically assembled from nowhere to help build this project and get it to the shape where it's right now. And so if you take a look at whatever metrics, commits, number of lines of code I've written, or impact or whatnot, you can see like I was very productive over the past months, and that's not even including a lot of the PRs that I've been contributing that are supposed to be integrated once we have Lemma 3 support inside the llm.c. Currently, it's just GPT-2 basically support. So how did it get started? Basically, Andrei tweeted out and said, have you ever wanted to train LLMs in pure C without 245 megabytes of PyTorch and 107 megabytes of CPython? No, well, you now can with llm.c. And so the idea is you want to have like an option to use a framework that's not bloated and that's efficient. But of course, there comes some trade-off in terms of flexibility that you have to accept for having that type of efficiency, okay? Which makes sense, hopefully. So what are some of the pros? The pros are this is a minimal code base, basically, where initially when he just tweeted this out, this was thousands of, just 1,000 lines of code, which is obviously very minimal. It's basically zero dependencies, it's just your C code. And it has very low overhead because it's C, it's not Python, it's not interpreted language, it's very close to hardware, right? And then the cons with this initial project was obviously, first, initially, it supported only FP32, so just the floating point 32 precision. It was only running on CPU, thus it was not as fast as PyTorch, obviously. But only a couple of weeks later, actually, it already became very, very efficient with 3,000 lines of code, with mixed precision support, with flash attention being supported. Although we were using external kernels, those were not custom written by us. But basically, you see some number here. The framework was already 46% faster than the stable version of PyTorch, and 7% faster than even the nightly version, which is, as you probably know, is where all of the experimental features are, some of which were not even going to get integrated into the framework. And so what are the pros here? Obviously, the same things apply: minimal, low dependencies, mixed precision. It now runs on GPUs, and it's faster than PyTorch, which is kind of a big deal given that it's just a couple of thousands of lines of code. You can run it wherever on a server without any special environment requirements. The cons are obviously lack of flexibility, as I mentioned. You'll soon see why. It's C code. It's kind of hard to make it extensible, change some flag, and have some new functionality behind the scenes without llm being as big as PyTorch, which we don't want to be. And then it's hard to find collaborators because it's hard enough to find people who are experts in ML and in LLMs, and it's even harder to find folks who know both Python and are prolific in C as well, and understand the low-level programming languages. So basically, where are we now? So 5 years later, after the initial publication of GPT-2, you can train GPT-2 1.6b, which was the model that OpenAI released back then, for $600 in less than 24 hours on a single node. So 8 GPUs, H100s, I think, is what Andrei used for this replication. But obviously, with more GPUs, you can do it even faster, right? It scales. So maybe a small tangent here. This was the release, I don't know how many of you remember, but back in 2019, this was the blog post that came out from OpenAI. And let me read it out to you. So due to concerns about large language models being used to generate deceptive, biased, or abusive language at scale, we are only releasing a much smaller version of GPT-2 along with sampling code. We are not releasing the dataset, training code, or GPT-2 model weights. While the misuse risk of 345 million is higher than that of 170, we believe it is substantially lower than that of 1.5B, and we believe that training systems of similar capability is already within the reach. Anyhow, that ties nicely into the current situation in AI, where you have a lot of these, let me call them AI doomers for lack of a better word, and then we had the SP 1047 bill and the European AI Act and all of those acts which are trying to kind of scare us. But like, I think this is a good example of how wrong we can be with like how dangerous these models are or they are not actually. And so fast forward to today, we can basically train such a model that civilization is threatening for $600 and nobody died, everything's fine. The civilization is still just running fine. Even with like Meta obviously now releasing much bigger models, like things are still going fine. Okay, so what makes LLM-C so efficient? By the way, let me just stop and make a digression. Like I prefer this to be interactive. So if you have any questions, feel free to interrupt me whenever you want. Just raise a hand, I'll stop and happy to answer your questions, just FYI. Otherwise, I could have pre-recorded the talk and it's gonna be probably better than me talking live. Anyhow, cool, make sense? Yes. Awesome. So what makes LLM-C so efficient? So there is no single answer, obviously. First of all, we are writing it in C and CUDA, which is very low level and high performant. Thus, you have less overhead. We mostly have custom CUDA kernels. As you'll see, we do use cuDNN, cuBLAS for a couple of kernels, especially for MATMUL, which is hyper optimized. It's very hard to get to the baseline that NVIDIA has set. So we do leverage some of those existing libraries. Then there is the communication computation overlap techniques, which are fairly common. It's just the HPC wider type of technique. It's not just for LLM-C, obviously. There is also kernel fusion. There is the mixed precision. There is the buffer reuse and recomputation. A ton of different techniques, and of course, just a ton of hacks that we kind of sprinkle around to make this all work. Okay. So let's kind of start the descent into the world of LLM-C. So first of all, we have to leave the TensorLandia, so to speak. We have to, you kind of have to forget about these nice objects that you can set. Like we have a 3D shape and we have all the metadata associated. You can call all these fancy functions, slicing, indexing, whatnot, on top of your tensors. You can do cool stuff like torch ones and then specify dimensionality and multiply by 7, -1/2. It's all very nice and close to mathematics. We kind of have to leave that behind. And also you have to understand that in PyTorch, when you do something like 1s plus 4s, in the background PyTorch automatically assembles the computation graph behind the scenes, and then you can nicely backprop through that computation graph when you're doing the backward pass. We kind of have to forget all of that and enter the linear memory buffers. We are back in the computer science first year of your studies, and you just end up with allocating with a malloc either on GPU or on host memory a linear array, and now you have to impose some structure on top of it so you can actually make sense of the structure. So, by the way, can you guys at the back row there see the snippet roughly? Is it visible? Some nods, okay. Sorry? 50-50, okay, that's, I'll take it. Sorry, go ahead. Do we directly copy to GPU memory? Depends. Some things are first on the host and we push them to GPU memory. Some things are directly allocated there. It really depends. It's kind of, yeah. You'll see some examples now as well. Thanks for the question. So, okay, let's kind of start. We want to train LLMs, right? First, we need to actually allocate the weights. We need to initialize the weights. And so we start by allocating first, before even allocating the array, we need to know what are the sizes of the layers we'll be using. And so you can see here param sizes of 0. We have VP times C. VP standing for the vocab size, the padded size, times C, which is the inner dimensionality of the LLM. And then we have param sizes of 1, max T times C, max T being the max sequence length you can pass into your LLM. And then all of the next variables you can see they are prefixed by L times something, L standing for the number of layers, okay? except for the last layer norm, which is basically the final layer norm weights and biases, and that's why we don't have the L prefix there. And so this is kind of the starting point for us before we start allocating. So now we want to reconstruct this, right? We want to have, in PyTorch, you would just call your torch NN. You would call embedding, you would call the modulus with blocks which are again defined using some primitive layers like linear layers or whatnot. And then you have layer norm. We want to just reconstruct this in llm.c, in pure C. Okay, let me go back. So the first thing we have to do is we have to allocate the buffer, and we allocate it here with CUDA malloc, okay? And then we have to put some structure. When I said put some structure on top of this linear buffer, so this is where it happens. We have a bunch of pointers, and so this is for example, the vocab table. This is the embedding layer. This is the positional embedding layer, and so we kind of have to, inside of this for loop, initialize them. And initially, you can see that how this logic works in the loop is you add plus equal to the previous size table I showed you. So that means that the initial pointer VTE, because we haven't added up anything, is just going to be pointing to the initial, to the starting address of this huge linear array we just allocated. And then with every single iteration, we'll be adding the elements and basically pushing the pointers across that linear array, so we have the structure defined on top of that array. Sorry?
This is still in the round, right?
This is, I think, will be basically define this. Whoops, I think it's CUDA malloc. So this should be on the. This is not malloc. Yeah, so it's actually on the GPU. And then let me kind of briefly mention this optimization technique we use. So we now have the weights, right? We have the linear buffer. We now have to populate it, right, with data. So we do that either by taking the pre-trained weights. And we kind of stream it from a file and read it into the buffer, or we have to random initialize it. In the case where we are using pre-trained weights, this is what we do. So you can do this in two ways. The most naive way would be, hey, we take the file from the drive, we load the weights inside of the RAM, inside of the host memory, and then once that process is done, we then start copying over to the GPU. But instead of doing that, you can add this small efficiency, which is fairly familiar for those of you who are familiar with operating systems, is you just add two buffers. And those buffers are much smaller than your actual file with weights. Those can be maybe 20 megabytes. I think that's the number we use. And what you do is you start streaming from start reading from the file into the read buffer. Once it fills up, you swap it, you make that the write buffer, and you start immediately copying the weights from memory to the GPU memory, while at the same time taking your file and continuing to write the weights into the read buffer. And so you can oscillate back and forth, you swap those buffers, and you keep on basically having a stream of data going from the file to the memory on the host all the way to the GPU. That's a small optimization you can do to make things a bit more efficient. And this was actually integrated quite lately, maybe a month ago into the framework. Before that, we just had it very dummy, like just because it's not something that bottlenecks your training. This happens before the training starts. It's not that big of a deal. But anyhow. And then there is the model init. This is a different way you can obviously initialize your weights. You start from scratch. And this is how the initialization function for us looks like. It's very messy and gnarly, as I said. The pro is obviously you have full control. It's so easy to change and make this do whatever you want without you having to rely on some high-level functions. So you have all the flexibility. But, well, actually, it's a lack of flexibility in the sense of if you now want to have k-meaning or some other initialization, you can't just switch a flag. You have to actually implement stuff from scratch. You have to know how to do this. You have to know C. You have to know how to implement the layer. So in that sense, it's lack of flexibility. Maybe I should have used a better word. So briefly here, what we do, we iterate over the L layers. And then we iterate over this number of parameter tensors, which is basically every transformer block has obviously the layer norm, the attention block, there is the MLP, there is also the layer norm there. And so that's kind of all of those layers inside of a single transformer block is what we iterate over in this second loop. And then what we do is you can kind of see it's messy. We check for index. If it's 0 or 2 or 8 or 14, all of a sudden initialize with all ones. And this happens because all of these are the 4 layer norms. And 1 is the default value, which makes sense because it's controlling the variance. And initially we want it to be at 1, and the biases are set to 0 by default because that the buffer that we initialize is just filled with zeros initially. Okay. So That's not everything. We still need the rest of the state for training LLMs. Obviously, you can't just have the weights. You need to have everything else. And everything else is you need to have gradients for the parameters. So we allocate it the same way as we allocate the parameter buffer. And you can actually see we also use the same variables here, param elements, param size of. And we also have this malloc and point parameters. So that's the function that allocates the buffer and then puts the structure of pointers on top of it. Other than gradients, we need activations, obviously. When you're doing a forward pass, you need to store those activations somewhere, and then later you'll need them during the backward pass. We have the inputs and outputs. You can see here the tokens basically have to be somewhere, and the targets are shifted by one tokens at the output. And there are also some helper variables around the losses. There is also the encoder backward pass, helper variables. I won't get into details, workload indices, and bucket info. And then we have the MV and master weights, which are basically the first and second momentum for the gradients, and master weights being higher precision weights because we are using Atom. Actually, we're using Atom W in llm.c by default. Any questions so far? Go ahead.
Hello. I see you use very specific CUDA APIs. Like, is it a stuff that you work on CPU or GPU, or is this all the specific code that must run GPU?
So all of this is basically CPU code. I'll show you some of the kernels. The kernels are really what runs on the GPUs, if that's your question. I'll actually dissect one of the kernels literally in the next slide, I think.
Okay, but you had a code like CUDA malloc. Is it just a stub? It would be normal malloc on CPU based, right?
You could malloc it first on the host, and then later you can push it to GPU. So it's not necessary. This code doesn't have to be GPU bound, like in that sense. It can be CPU, and then later you can do it. But like it's more efficient to immediately push stuff on the GPU.
Okay, just quickly related to it, like, is it flexible enough to move to, for example, AMD ROC library that supposed to be a general GPU compute?
What was the question? Sorry.
Like the AMD ROC library kind of provides GPU optimization, computation. Like, is it easy to migrate to it, or?
Good question. So the design decision we made was we don't want to bloat the framework by supporting different. We just focus on CUDA. It's just NVIDIA GPUs, but community has been adding a ton of cool projects. There is the AMD fork actually. The person that is building that fork is in the server with us, and he already got reached out by AMD and got some offers and stuff. So they care about this as well apparently. But yeah, great question. Thanks. So quickly, I know this was overwhelming. Obviously, I don't expect you to understand all the code. I just want you to follow me like on a high level. But if you want to understand what's going on, the best way, and this is the way I approached it, is just draw stuff out. Like I would open up VS Code, set it into debug mode, start stepping line by line, and understand. For example, I just saw what's every single buffer that we allocate, no matter whether it's on the GPU or on the host memory. So all of these that are kind of in these contours, all of these are on RAM, and the ones which are not, they are on GPU. So you can see here we have the gradients, we have the params, we have the activations, we have even some cuBLAS workspace with 32 megabytes. We have the MV and I guess the master weights here. So like it just helps you kind of consolidate and understand what's going on in the framework. That was more of a tip and digression there. Okay, so we have the state, we have the weights, we have everything to start training, and now the training loop is, I mean, familiar to all of those of you who've ever written anything in PyTorch or TensorFlow, whatever, Keras. So mainly here we have these four functions. We want to do forward, backward, including the reduce step across the GPUs, because our code supports both multi-GPU and multi-node. Actually, multi-node is something I've supported. I'll talk about it a bit later. And then we want to calculate the gradient norms. So because we do gradient clipping set to 1, and then we have the update of actually updating parameters with those gradients. So quickly here, we have a for loop that's doing, we have microsteps because this is gradient accumulation. This is basically a way for you to effectively end up with a bigger batch size. Even if you don't have enough VRAM, that's kind of the way you do it, and it can be easily shown that this is completely equivalent to you just running a big batch on a bigger GPU with a single forward pass. This is completely equivalent because we keep on depositing and adding up the gradients on top of the existing gradient buffers. So what we do here in the loop is we just load the tokens into the buffers. We do the forward step, as I said, backward and reduce. We'll get to that in a second. And then you can ignore the detector stuff. That's Andrei's ad hoc solution that he just coded up to detect when we have outliers, and then we just skip the steps when those outliers appear. Just simple statistics. We track, I think, standard deviation or whatnot of the values. And if it's just too outside of the expected range, we just ignore it. And here you can see inside of the is fine at the z loss, blah, blah, blah. Here we just skip stuff. Anyhow, we could compute the gradient norm, and then we have the update step. So let me just continue here. So here's the forward pass. You're used to seeing the syntax to device, and this is how it actually looks like when you go down to C. We have some CUDA mem copy operation, and we copy from the input buffer, which is on the host memory, to the model inputs, which is on the GPU, and you can see here the direction of the copy operation host to device. So let me walk you through the forward pass quickly. So the first thing is we obviously do a for loop over all of the L layers of the transformer. And then we first have this conditional statement, which basically, depending on whether we are on the 0th layer, in that case, you basically start with the encoder. So the encoder output is going to be your value that you're going to allocate for the residual. And then in the next layers, you want to offset inside of this residual tree a buffer, and you use L-1 to offset by BTC, because that's how many tokens you have per layer in that buffer. And then similar logic here, we have some offsetting going on, because you want to position yourself in. So remember, again, we have that big linear array. We have it chunked up so that every layer is basically responsible for a single chunk. And then inside of that chunk, we have L sub-chunks, because each of those are the weights for that particular layer, okay? For that particular transformer block. So that's why we have to offset stuff in the parameter buffer, and then here in the activations as well. And there is a couple of optimization tricks here. One is recomputation. So you can see here these recompute expressions, the ternary operators, which basically, if you take a look at here, you can see ln1 plus lbtc. Otherwise, we just have lnf. So we just reuse the final buffer instead of having L times B times C. So we can basically save up a lot of VRAM by doing these types of recomputations. The trade-off obviously is, yes, you have a lower VRAM consumption, but you will have to recompute that same information later during the forward pass. That's kind of the trade-off you're making there.
So is that the gradient checkpointing trick?
It's basically the same idea, yeah. It's different in the sense that gradient checkpointing, you usually have some periodicity in how you save your checkpoints. For example, you just save for every single transformer block, you just save the input activations or whatnot. It's similar idea, basically. It's the same idea, basically.
I see. And one more thing. So when this linear memory that you first allocated, that was for weights. But not for activations, right?
We also had it, if you remember the slide with the state, we also allocate for the activations, and for all of those buffers are already.
It's for activations and also for Adam-related stuff, right?
We actually do some allocations ad hoc. I couldn't show you everything, but for example, I didn't show you the activation gradients. I didn't show you that. That's going to be done ad hoc. The first time we call in a lazy manner, we're going to allocate the buffer in the first pass.
So these are these float values for activations.
So float text is, by the way, float text is this generic data type that can be either BF16 or FP32. It's a compile time constant that we can change. And then these are the activations, yes. Actually, we kind of have messy syntax, so forgive us about it. We have to refactor this, because I would rather have like A or something here and then wait here. But Andre, actually, I'm going to blame it on him. He proposed this syntax initially, so we just stick with it. OK. And then we have a buffer reuse. You can see here we have this scratch buffer, and a lot of the intermediate computations that we don't need later during the backward pass, we can just do all of those in that same buffer, and by doing that, again, save some VRAM. So those are all some small tricks we use to basically make this framework as efficient as it is. And then, so finally, once that is done, once we have done the offsetting, we just now call a ton of functions which are wrappers around CUDA kernels. So now this is just a lot of hyper-optimized code that's made to be run fast on GPUs. So let's kind of dig into one of those. This is how the launcher, the kernel launcher, is going to typically look like in our framework. So first you'll see something like block size. Block size is this variable that you want to optimize for your particular GPU you care about. You usually do some benchmarking. You'll see where is the peak in terms of throughput for your particular GPU, and you can hard code that one here. In practice, how it looks like in PyTorch, good folks at NVIDIA have built a ton of these different kernels with different block size values. And though what happens is, depending on your tensor sizes and various different things, the dispatcher in the background chooses just the right kernel for just the GPU you're running. And so this is kind of very optimized by NVIDIA. But in practice, that means you have to bloat up your so to speak, repository of kernels. You'll have to have a ton of them for different GPUs. Here we can just have a single kernel and make things easy. Okay. So after the block size, there are some CUDA specific stuff. I won't go into too much detail, grid size and block size. 0 means we don't want to allocate any additional shared memory. And then streams are just this concept in CUDA where on a single stream the computation is done sequentially, but in multiple streams they are not going to be blocked by each other. They're not synchronized unless you want to explicitly synchronize them. They just run in parallel and independently from each other. And then you basically dispatch a kernel. This is the syntax that is used for CUDA. These 3 smaller than and 3 greater than signs, and I also already mentioned the arguments. And so here is the actual kernel. This is the simplest kernel you'll get. These element-wise kernels are quite simple compared to, for example, layer norm or softmax. Some of those can get very gnarly. And so here's a couple of ideas here. First of all, you can always compute this index, which tells you how to index into the array that you're trying to process. You usually have the guarding logic. We don't have it here because we didn't need it. We knew that this is never going to go outside of the size of the array. But usually you have some if condition there, checking if index is bigger than n, then just continue, skip this. This thread can kind of leave the context and not execute. And then next up, we have this load operation. I'll get to the 128-bit in a second, but the CS part stands for cache streaming. And what you're saying here to the compiler is basically, hey, please do not cache these activations because we will not need to reuse them later, so no need to store them in cache. And thus occupy a cache with some values that we don't care about and makes things slower. So that kind of tells you how you have to think when you're programming in these low-level languages. You kind of have to understand the architecture. You have to understand the hierarchy of memory and a lot of details like this to make actually performant CUDA code. And finally, actually, let me go back here. The main idea here really is this 128 part. So that means that instead of loading a single float or a single BF16 number, so 16 bits, or FP16 or whatnot, instead of that, you always load 128 bits. And so in case we are operating with BF16, that means this translates to 8 numbers being loaded at the same time. And then we have a for loop where in local registers, we just process and do the JALU logic here. This doesn't really matter for the sake of my discussion, but you can see it's much more efficient to pull it once and then do a bunch of operations like on the GPU as opposed to loading multiple times and going to the GPU VRAM, which is very expensive operation, and typically you're trying to minimize that. And that's why flash attention and methods like that work really. They try to minimize the number of accesses to the global, to the VRAM.
One more clarification. So here you are talking about loading from GPU RAM to GPU registers?
So here we are loading from the HBM, so from the VRAM, which is the global memory, into the, well, let me just think here for a second. This is the SRAM, actually. This is the SRAM on the streaming processor itself. And there is also the shared memory, which is kind of the cache, the level above in the hierarchy, but below the...
Everything is inside GPU.
Everything is in GPU, because these are kernels. So everything that's, I think there's, yeah, when you see global and these things like __ device, all of those are only run on GPU.
This is where you need understanding of the structure of memory inside the GPU.
Yes.
So that you know from which type of memory to which type of memory you can go
exactly
forth, and what is the optimal size of this transfer, and that's where 128 comes from. Exactly,
and in the launcher as well, as you saw the block size variable. that's also where you kind of have to know stuff about GPUs, because before you call the kernel, you have to specify its parameters, and that's where you also need to know a bit about GPUs. Yeah, but this is not a representative kernel to show you all the tricks. This is the simplest one, and that's why I've chosen it, because it's... How many of you, by the way, can you raise a hand, how many of you have ever seen CUDA code? Or, okay. Seen CUDA code, maybe 50-ish%. Written CUDA code? I see one brave soul. Okay, good to know. Hopefully I didn't lose you too much, but it's on a high level. If you've done anything similar, should be understandable. Okay, let's continue. How am I with time, by the way? 30, awesome, I have enough time. So backward pass, let's go here. This is one of the main techniques that you need to know of. Fusion, this is something that PyTorch heavily does. The compiler in PyTorch does this. And so it's a fancy word for basically saying we want to cram in as much things as possible in a single kernel, as opposed to launching multiple kernels. Because every time you launch a kernel, it's not like a zero cost operation, you're paying for the overhead. And so you typically want to cram inside a single kernel as much as you can. And in this one, this is a kernel we call inside of the backward pass. But look what we do in that kernel. We do actually the end pass of the forwards, the final step of the forward pass, the softmax computation is actually done here in this kernel inside of the backward pass, which is kind of, if you think about it, it's not something you're used to when you're writing a high-level PyTorch code. But efficiency-wise, this is what makes sense. And so once we have the probabilities, then we can compute the losses. So cross-entropy, so we have minus log of prop. That's the second step. And then the third step is we actually kick off the backward pass inside of this kernel. And that happens right here. In particular, there is the prop minus indicator times the loss part. So this is what cross-entropy is kind of very neat, that it reduces down to this very simple expression. Indicator is just 1 when you have the ground truth token index. Otherwise, it's going to be 0. And then the loss because we're computing the local gradient here. So that's kind of the concept of a fusion. And then I mentioned previously in the forward pass this recomputation step. And so here you'll see how it actually looks like in the backward step. So if we were in that mode where the recompute was set to 2, those are some local numbers we're using. Treat it as like we are now in the recompute mode. And basically what we do forward. So that's because, remember, we just have a small buffer. As opposed to having L slots in the buffer, we have a single slot, which means we've lost most of the information and we have to rerun the forward step now during the backward step. And that's the trade-off you're making. And as you said, it's very similar to gradient checkpointing. I would have to think about it a bit, but it's conceptual, it's literally the same thing. Okay, and then one more technique that's very important and used quite heavily everywhere in deep speed in many of these libraries is the fact that you want to overlap communication with computation. And so when we're doing this backward pass, so when you process, because it's backward, right? We start from the last layer. And so once we process and compute the gradients for that last layer, then asynchronously, we just kick off this operation called multi-GPU async reduce gradient, which is going to basically start reducing the gradients of that last layer across your GPUs, assuming we have a single node. That means the 8 GPUs are going to be communicating the last layer's gradients to each other and reducing them. By reduction, I here mean they do average, so you end up with valid gradient values. And this is not blocking, that's the important bit. That means you just trigger this function and you start processing the penultimate layer. And now all of a sudden you're computing the gradients of the penultimate layer. And once you finish that, then you kick off again the async operation of doing the reduction. So by the time you come to the end of the backward pass, you also have the reduced values across the GPUs, as opposed to what's the alternative? Well, the alternative and the easiest thing to implement is just do the backward pass. Once you're done, kick off the reduce operation. But now you have to wait for the reduction to happen, and that's slow. So this is one operation that people use quite heavily. Digging a bit deeper inside of this code, well, I don't think you will be able to see that. Sorry? Can you hear me? It died? Okay, let me try and...
Too much code. Too much C code. It couldn't handle.
Too much? Okay, it says on now, but you don't hear me.
Yeah, I think the audio system died.
It's sentient. We're I can talk loud. I don't know if you guys hear me, but I think
it's bad.
Okay, perfect. Cool, I killed the microphone. Or C killed it. Yeah, I don't know if you can see this, but the point here is I just went inside of this function, the reduced gradient function, and now depending on which zero stage we are in, we currently support both zero stage 0 is basically your DDP, distributed data parallel. Zero stage 1 is when you have when you're sharding your parameters. Zero stage 2 when you're additionally sharding your gradients. That means that not every GPU has to have all the gradients or all the parameters. They can have just like if you have n GPUs, one of the GPUs can only have 1 over n parameters, and then you can kind of do the gathering operation so that it can get all the other parameters when it needs on demand. But now, depending on the zero stage, the all reduce can be very simple, or it can be a bit more complex, because in the situation where we have zero stage 1, that means you just have a local shard of the parameters. That means that GPU doesn't really care about all the gradients. It just cares about the shard of gradients, and then you just have some offsetting logic here. I don't even see it myself, so hopefully you probably don't see it as well. But anyhow, that's kind of that operation. It doesn't really matter that we go into too much depth. The way you understand this is the same way I did, I think, and that's just by drawing stuff out. Like, it helps a lot, and it actually helped me catch a couple of bugs when I just joined the folks end of May working on this, and I really recommend you do this.
This is DDP.
This is DDP in case we set zero stage to be 0. You can't see it in the config, but it can be DDP or it can be zero stage 1 or 2, which are different things. So DDP just means that every single GPU has the whole gradient vector and the whole parameter vector, and when you do the all reduce, you just do average across those whole vectors, as opposed to just looking at the chunks like shards of those vectors. That's the main difference, really. You're saving up memory by doing it, right? Because every GPU needs to have 1 over n less of buffers.
How is this related to FSDP?
FSDP is similar. I don't know. I would have to sit down and take a look at the definition again. I did read the FSDP paper. There are some subtle differences. On a high level, it's very similar. Whether you shard the parameters or gradients and what you communicate over, all of those details matter. And
so
yeah.
You save memory, you add a lot of communication between GPUs because of that, right? I mean, in regular DTP, you synchronize only after the entire backprop happens. And in FSDP, you have to synchronize after every layer, basically.
I think that's optimization detail, because that's what I showed you with the overlap of communication. Where it's just the total volume of communication will not change by doing this gradual type of reduce operation I showed you. It's just going to make it more efficient in terms of speed. You don't have to block and wait for the reduce operation, but the same amount of gradients need to be exchanged still.
You have to bring in the weights in FSDP. Like in DTP, every GPU always has all the weights. But in FSDP, you split the weights into GPUs. So at every layer, you have several shards. And if you want to compute the forward pass of this layer, you have to bring back the weights from the other GPUs to do the forward pass and drop them. And then next layer again, bring back and drop them. So the
getter operation before. But the thing is, there is so many of these techniques, and the differences are subtle.
So this is that kind of thing?
That is that kind of thing, yeah. And okay, let's just kind of chill now and let go the C code. And here's, let me show you some nice graph. This is how the presentation is supposed to look like. I show you some high-level results. It's very cool, no code, no messiness. You come out being very happy, understanding everything. So here are the results. Andrew actually ran this one. 24 hours, as I said previously, $600, one node. You can see the curves are fairly stable. Actually, once we go, we do have some instability issues. I'll address that a bit later with the MIUP PR I was building. We did have some occasional spikes later when we were training on like 300 billion. I think it also has to do with the data set we use. I think we kind of transitioned to the fine web Edu data set, but we still have some instability issues. But you can see here we are outperforming both GPT 2 and 3. Eval numbers, again, take this with a grain of salt. those weights were trained back in the days 2019, so there is a distribution shift and all of that, but like it's still valid result, just not completely apples to apples. By the way, forgot to mention, somebody asked, I think, basically as I said, there is support for AMD and bindings for many different languages. You can just see in the bottom of the README, the forks and the community contributions. You can find all of those on the GitHub repo. And people have already run with llm.c with hundreds of GPUs. And I did add support for multi-node training, so all of that is already possible. Okay, so quickly focusing on some of my PRs. The most recent one was I added support for llama 3 in Python. I helped make our code bitwise deterministic. By that, what I mean is when you're training your LLM, you're occasionally saving checkpoints. And if your training run fails at some point, you want to be able to roll back to the last checkpoint and start training from there, obviously. That's just the classical checkpointing stuff. So the bitwise determinism part means that we have a guarantee that if you start from that checkpoint, your loss, your gradients, everything is going to be bitwise the same, precisely the same as if you were to just be still running that first run before the failure. So that's kind of a very neat property and not something you can take for granted because GPUs are inherently, well, not even deterministic, plus this dispatching logic where kernels kind of change if you just change the shape of your tensor a bit. And so you can really guarantee this behavior is very, very nice to have. I mentioned multi-node support, random shuffling. Whoops, this is for some reason jumping over. Sorry. Go back. And then I just help with bug hunting quite a lot. And again, the way I've done this is just I stepped through every single line and draw stuff out. And I realized, oh, this doesn't make any sense. Like, guys, is this error? And then they were like, oh, yeah, this is actually a bug we have. And so like, I really recommend that as a process for learning about new code bases. And then there is again, just briefly, the difference between GPT-2 and Llama 3 is not that big. There is only a couple of architectural changes that have happened since. One is SVGLU, which is basically the gated logic in the MLP. Then there is the GQA. There is the well, KV caching is not like it's just an optimization technique. It doesn't change anything. And then the last thing is rope. Basically, that's kind of 3 changes that we have introduced since 2019, which is not a lot. And the results I got with SVGLU, the blue curve here, you would say, oh, this is really good. Like, we should definitely switch over to SVGLU. But what I didn't tell you here is I didn't account for the number of parameters. So by adding this additional linear layer that acts as a gate, I bloated the number of params. And we know from Beta Lessons by Rich Sutton, as you add more parameters, more compute, more data, you get better performance almost always according to the scaling laws. And so this is not fair. And so when I make it fair, you can actually see now, so the blue curve is this unfair one, so to speak, and then we have the orange one, which is the new SVGLU. When I account for the number of parameters, so they have the same, the green and the orange have the same number of params. And you can see the convergence is much faster with SVGLU. But as you get to the end of the run, the slope is even worse compared to the green one. So I would argue that actually just using Jelly is even better than SVGLU, at least in this particular case. And this ties nicely to this paper from Noam Shanzir and others, Sharon Ereng, who is now, I think, in Meta. Anyhow, so do transformers modification transfer across implementations and applications? And the answer they found was, surprisingly, we find that most modifications do not meaningfully improve performance. That's kind of the general statement that we observe over the last many years of exploring transformers. And like one notable exception is rope, which I mentioned. You can see the results here. So the blue curve is a rope, and there are no tricks here, no additional parameters because rope doesn't introduce parameters, it just rotates the pairwise tuples of your vectors. And basically, you can see much better results compared to the orange, which is the positional embedding of the GPT-2. And finally, you might be surprised the green one is without any positional embeddings, because transformers can still learn stuff about quote-unquote world, even without positional information. And it's interesting that the difference between these two is smaller than between rope and positional embeddings there. Okay, and one more thing, I've added KV cache support. This is something I'm really bullish on. Like, I think efficiency ultimately is the make it or break it type of a thing. And here, like I showed that I have 6x improvement with 124 million model, and 1.5B is already 12x. So you can assume as we increase the scale here, you'll get more and more benefit in terms of the speed up of sampling with KV cache. And like this is again ties back nicely to Bitter Lessons by Rich Sutton, that like just leveraging computation, being more efficient, and we saw that with more tokens, more parameters, greater scale come the results, and algorithms that can leverage the scale in some way are the ones that win. And this is the last one. I'm going to kind of skim over this one. I try to replicate MUP. The end result is that, yeah, it kind of works, but then again, the loss is not really as good as we expect it to be, so we didn't really integrate it. Stepping back for a second, the premise of MUP is the following. Instead of doing a very expensive hyperparameter tuning of your 7B or even bigger models, which is obviously very expensive to find optimal hyperparameters, instead what you do is you reduce the size to, for example, 100 million params. Then you do like a much more extensive hypersweep analysis. You find the optimal hyperparameters. And then this technique guarantees you, if you parameterize your LLM in a certain way, that those same hyperparameters that were optimal for 100M are going to remain optimal as you scale up. And that's a huge promise from the MUP line of work. And here you can see what that means in practice. So you find a learning rate that's optimal for one of the models that are like maybe smaller width, maybe 128. And then as you keep on increasing the width, as you keep scaling the model, you can see that you kind of pull the vertical line here, and we have a stable optimum for the learning rate. That's the promise. I've done these coordinate checks, which are basically the equivalent of a gradient check for the MUP, and you expect the curves to kind of be flat, because what these represent is on the x-axis means we are scaling up the model, and as we are scaling up, these L1, the mean L1s of intermediate representations are not exploding. And here in the standard parameterization, you see that's not the case. You can see the explosion, and that's why it's less stable than MUP. That's kind of the promise on a high level of MUP. These are the curves I actually got for us. It looks like we have that stable optimum for the learning rate. But as I said, the thing is these curves are not low enough. So the loss is worse than what we get with standard parameterization. And this has been a pattern I've heard. I talked with the Gen AI lead at Meta working on Llama. They told me they also tried MUP. It also didn't work. But then I recently saw some guy building diffusion models, and he made it work. So it might be that for transformers, it doesn't work as well as for diffusion models. Well, diffusion models now use our transformers themselves, the DAT. Anyhow, it's kind of open question. If you want to contribute, I actually have a PR open, and I wrote a mini tutorial on how this works for a practitioner, because MUP is really one big mathematics appendix of a paper. Really, the author is the mathematician by profession, and so it makes sense. But it's really a lot of the maths you really don't need. You just need like a receipt, like a cookbook, what I need to do in order to implement MUP for my LLM. Couple of anecdotes here. When I was training some of the runs, we just had these weird spikes. I immediately observed that the training losses are actually, the curves are fairly stable, so I assumed immediately that this is just some glitch in terms of us not cleaning some values. It turned out we were just not cleaning some buffers, so I caught that bug and we fixed it. And then this is more of an internal joke, like where the fact is that no matter how state-of-the-art your framework is, you always have a while true loop that makes sure everything is running smoothly, otherwise things just break. And so basically the watcher, the while true is what makes, this is the watcher for llm.c project, okay? And yeah, finally, again, two tips if you want to get started with llm.c. First, I really recommend you open up VS Code or your favorite IDE, maybe Cursor now, who knows, and then just start stepping through the code base and start drawing stuff out, and so you can form a mental representation of what's going on, because it can get overwhelming, especially when you join now, when the code base is now more than 1,000 lines of code, and it's kind of gnarly when you start looking at all the kernels. But yeah, those would be some of my tips, and I've been showing some of these drawings I've been making over the past months, and other folks found it helpful, including Andre. So yeah, with that, that's kind of all I had.
Thanks a lot. So these drawings are available?
These drawings are my IP. Sorry, I will be selling them for a $5 subscription on a monthly basis. I'm joking. You can join our Discord and you'll find them in the history.
Sure. Let's start from questions.
Thanks a lot, Aleksa. It was great talk. A question regarding bitwise determinism, right? We all know that basically generally float numbers are not associative addition and multiplication. How did you manage to, or maybe if you explain, I would understand.
That's a good question. There's been multiple components how you make this work, and I don't think I can give you a concise answer. How, on a framework level, how do you make sure that everything is bitwise? Because a lot of the components can introduce this type of non-determinism behavior. I think one of the things, let me think, atomic adds, like we have to make some stuff sequential so that yes, it is not associative, the floating point summation operations in general, but if you make sure that they are in some order which is predetermined, then you always end up with the same result. As opposed to them competing. As opposed to them competing and writing in parallel, and so who comes first blocks with the atomic operation, and then if you do that, then you'll end up with different results. So yeah, that's the best.
So you are sacrificing some performance, but you get determinism.
I don't. We might have made some small trade-off in terms of performance, but I don't think it was. I think it was negligible, if I remember correctly.
Thanks a lot.
Thanks.
A follow-up on that question. So, when you want to store BF16, you have to be careful to have this consistency. You have to be careful to not convert it into other type of float before storing on the disk, right? Is that what?
Well, you never want to convert BF16 into float because the thing with BF16 is it has a very high dynamic range, and that's what makes it have a much bigger advantage compared to FP16. And so basically you can represent a much bigger range of numbers, but you lose some of the precision. That's kind of the trade-off you're making. So you can't really convert nicely. You can, but like you shouldn't do that. If it's BF16, save it as BF16, load it as BF16, process it as BF16.
Okay, so but I mean, the CPUs do not directly support BF16, right? You probably just keep it as sequence.
You can, I mean, ultimately it's just unsigned int. You just have some, you know the semantics of the numbers. So if you want to do some processing on the CPU, you can do that. You can just cast it as an unsigned int and treat it as like, you know where what each field means, what's the sign, what's the mantissa, what's the whatever. And so you can process it like that. But yeah, usually, I don't know whether we had to do anything along those lines, like process BF16 on CPUs. Did you have any use case in mind? Why would you manipulate?
So the entire thing happens in GPUs. I think in some PyTorch implementations, you would, when you're writing code and you have this flexibility, you do random things, right? You could do some non-differentiable operations on CPUs, or I don't know, convert it to NumPy and play there. But all those things probably don't exist here. You do everything in GPUs and you like bitwise store on the disk and then reload. And
yeah, mostly if it's something that you can parallelize, then GPUs are unbeatable. You just want to do it there. You want to use those streaming multiprocessors and pay off that money you gave to NVIDIA, so you better use them.
As you mentioned, there are very few C developers now, even fewer C developers who know transformers. When do you think you will be able to pass this work on to an AI C developer and spec relax and AI developer will continue?
Yeah, I mean, there are bindings. You can use a Python binding and never touch C. It's the same with PyTorch, right? Most of the framework is just in C and CUDA, but like you just see the Python API.
It was not that serious. It was like, do you know in 1 year, 2 years, 5 years, we will have an AI developer that can write C code?
I think we already have it, honestly. Like,
and you will be able to pass your work to that developer?
Did you try using like some of these like Claude for coding, for example, over the past period?
Yeah, but not too much now.
Okay, I did. I started actually building some app, but it's a caveat. It's a web app, so it's not like AI code. So there might be more data for web. And I'm actually really surprised. I was using Cursor. I was using Claude by default, and I honestly, I'm treating it as an intern. I kid you not, I'm not overhyping this. Like it's literally, I give it a task, it does something, I just review it. Most of the time it works, I just check it in. Sometimes I just give a further suggestion, and then I submit it. And so it's literally, we are getting to a stage already with coding assistants where, at least in some of the languages in particular, there I'm using Next.js, JavaScript. I don't think we have plenty of C code available on open source GitHub repos. I'm fairly sure. I haven't tested for C in particular, but I will be surprised if it's not good. And if it's not good now, wait a year or 2 years.
Also, you are so positive. I'm like, now I have to check it out.
You have to. I didn't believe the hype myself, like because I was mostly using ChatGPT or Claude UIs. So I would do something and then just like use it as Google, right? But when you have an integrated environment in an IDE, and there is so many cool things you can do. I didn't even think about it, but some people are actually paid full time. There's a startup doing that full time and thinking through all the features you can do. So like there is a ton of cool stuff they've done. Like for example, when you're writing code, you just select a section, type Ctrl-K, and then start interacting as if it was ChatGPT, and you ask it for either comment, explain me this code, or modify it. It does that in place. You just Control-Enter it, and you accept the code or you refuse it. You also have the chat on the side where you can link it pages inside of your code base. So I say, hey, please implement me this handler and use as inspiration this file. And I link the file. It reads the file and just like has all that context. You can also link web pages. It reads a web page, gives you an answer. Really powerful thing. And so I think for C it's going to work as well. There is no reason why. Maybe even better because it's so structured and low level and so like very, I don't know. It's probably less messy than JavaScript because it's strongly typed. It's just like much stricter syntax. Like what I'm trying to say, I guess, I would bet that online there is more correct C code than JavaScript code. And not just because of the language, also because of the demography that attracts C versus JavaScript. That would be my bet. I would have to, yeah. Go ahead.
Thanks for the great talk.
Thanks.
The slides get so technical, it's legendary. My question is on the, I like that double buffering trick. It's quite elegant. I'm wondering why do you need to go through the host memory though? Isn't there an API to go directly from disk to the accelerator RAM?
That's a good point. Honestly, I'm not sure. That's something that NGC 92 has done. I've just reviewed that particular PR. It might be possible. I wouldn't be surprised. Although directly from drive to GPU, I don't know.
That's from network.
Maybe from network to GPU.
Exactly. Actually, there should be some API. I don't know if anyone uses it, but there is a support for independent connected nodes to so that the GPU can read through network from another node. So I'm sure there will be something from the disk on the same. But I don't know the use cases.
Yeah, makes sense. The thing here is like this happens before the training, right? So people don't really care that much about efficiency there. Of course, you do care about stuff like uploading checkpoints. You don't want that to slow down your cluster training. But yeah, it would be cool to see whether that exists. Good point.
One more question from me and then I'll get. So in Llama 3 paper, there was a paragraph that was described that when the training algorithm is trying to save the checkpoint on the disk, all GPUs are kind of free, right? At that point, they don't do any computation, and there is a drop of 10 megawatts of power, which is a problem for the electricity grid. So the question is it possible to do this thing asynchronously so that the GPU training continues, but this I/O part that is saving the checkpoint does not stop the GPU process to help the electricity? I
don't see why it's not possible. Like I guess it just depends on the infrastructure constraints. And the thing with these, the thing here is that all these clusters are so specialized. That's why Meta cannot release their code base, by the way, like because it's very specialized to their particular infrastructure. And so all of them have, when you get to that level of optimizing these huge runs, there is a lot of different differences between clusters. And so in theory, why not? Like you can just kick off a background thread that's going to be uploading a checkpoint somewhere where you keep on getting your GPUs busy. So like
keeping it consistent, like if you're saving the first layer, you don't want to update the second layer before you save the second layer. That's why you have to stop with that kind of synchronous.
No, but good point. Yeah, I would have to sit down and think it through, honestly. But that's a good point. You might have some race condition there that you have to block it and make it atomic.
Just more an engineering question. Would you write such kind of project in Rust because it would give you more safety, or there's too much row pointers and you'd rather make it less harder?
I've never used Rust. I know that XAI now started using it in a couple of these big, good AI startups. Is it more safe than C, and how can that be?
It is. You can
It is.
double free and a bunch of other things. There's less.
Okay, I mean, kind of stupid on my side. Like, of course, C is unsafe because you can, for start, you can have memory leaks and all of that. But you have all the control, and if you use smart data structures, if you're using C++, smart pointers or whatnot, then you get some extra safety. I've never done Rust myself, so I'm out of my depth there, so I can't really comment on Rust.
But I assume you run sanitizers and memory. Like when you do CI build, there are sanitizers. You make sure that like you're not reusing, like you're not using buffer that was deallocated. Right?
So what's the question? Sorry.
Like, do you use sanitizer as a part of your CI/CD pipeline?
We don't do any sanitization. And by that, what do you mean exactly? Can you clarify the?
For example, part of LLVM, right? You can say, hey, let me compile this every memory allocation, run an application, and see whether someone tried to access the memory that was deallocated, right?
Yeah, we are a bit more YOLO than that. That's a good point.
Thanks.
Thanks.
Let's thank Aleksa again.
Thank you.